Welcome. Today's lecture is about supernovae, explosions of stars. There are different kinds of stellar explosions, and astronomers have tried to classify them. Since astronomers are very imaginative, they've called them type 1, type 2, etc. Type 1 supernovae, for example, have been further subclassified, again very imaginatively, as type 1a, 1b, 1c, and so on. Now, the distinction between different kinds of supernovae is made on the basis of two facts. One is the nature of the light curve, the rise and fall of the intensity of radiation from the supernova. And secondly, on the elemental abundances as inferred from the spectrum of the ejecta. Now here are two classical light curves. On the top is the light curve in the solid line is the light curve of what is known as type 2 supernovae. There is a sharp maximum, then there is a plateau, and then there is an exponential decay. Type 1 supernovae, on the other hand, the light curve rises to a maximum and starts decaying exponentially, and there is no plateau. The exponential decay of the light curve is a clear signature of radioactive decay of elements that were produced during the collapse of the core. Now, here are three light curves of type 2 supernovae, and what I wish to highlight here is that the spectrum, as I shall show again, is very rich in the hydrogen line. Here is the H alpha line, here is the these are H alpha lines of these three different supernovae, and then you have H beta, H gamma, and so on, as I shall now try to show you. Now here is the spectrum of a typical supernova ejecta in all its glory. You see a tremendous number of elements. You see helium lines, oxygen lines, neon lines, iron lines, argon lines, and so on. And most prominent, of course, is the hydrogen line, which is shown over there. That is the H alpha line of hydrogen. And these are iron lines that you shall see. Now, look at this particular spectrum from a type 2 supernovae. What you see are three prominent hydrogen lines: the H alpha line, the H beta line, and the H gamma line. So the hydrogen is clearly very dominant in the ejecta of this particular kind of supernovae. But let's look at the bottom light curve. In contrast, there are no hydrogen lines. On the other hand, you see strong helium lines. Okay, so some supernovae have no hydrogen lines, but strong helium lines, and we need to understand this first and foremost. Now before we do that, let's pursue this business of different types of supernovae for a few moments more. Broadly speaking, we may distinguish the different types of supernovae as arising due to the explosions of a massive star or the explosion of a white dwarf which is pushed over the Chandrasekhar limiting mass. Type 2 supernovae, type 1b and type 1c, can be termed as core collapse supernovae resulting from the implosion of massive stars. So these supernovae occur when the core of the star implodes and the gravitational binding energy released explodes the rest of the star. Type 1a supernovae, on the other hand, is associated with the explosion of white dwarf, which is pushed over the Chandrasekhar limiting mass. Now let's first discuss core collapse supernovae, because these are far more common than type 1a supernovae, although they are tremendously important as we shall see when we discuss cosmology. Now, that takes us to the subject of explosions of massive stars. Supernovae of type 1b and type 2 are explosions of massive stars that are triggered by the formation of a neutron star right at the center of the star. And the mass in the ejecta could be as large as 5, 10, 15 solar masses, because the neutron star has a mass of only 1.4 solar mass, and the rest of the mass is thrown out into the interstellar medium. Now, the initial velocity of the ejecta can be extraordinarily high, typically of the order of 20,000 kilometers per second. How do we know this? You determine this from the Doppler shift of the lines such as H-alpha line, H-beta line, or the helium line in the case of different types of supernovae. Now, why are the ejecta expanding at such incredible speed? That's because an enormous amount of kinetic energy is imparted to the exploding ejecta. The amount of kinetic energy is of the order of 10 to the power 51 ergs. But please remember, this is a very small fraction of the energy released when a star explodes. When a neutron star is formed, the binding energy that is released is 10 to the power 53 ergs. So only 1% of it goes into the kinetic energy of the ejecta. Now, the expanding blast wave will drive a shock in the interstellar medium because it is traveling with a speed far greater than the speed of sound in the interstellar medium, so it will drive a shock wave into the interstellar medium. More about this towards the end of this lecture. Now, let us consider massive stars, more massive than, say, 10 solar mass. We have discussed all this in great detail. So let me recall for you very quickly. What happens at the end of the nuclear drama, the final act of the drama, is that the core of the core of the massive star looks like an onion with different layers. Right in the center, you have an iron core, which is formed when silicon fuses to form iron group of element, iron, nickel, and cobalt. Now, in this reaction, there is a tremendous neutrino luminosity associated with this. The neutrinos cool the core, and therefore the core quickly becomes degenerate, in the sense that the Fermi energy of the electron is far greater than the thermal energy kT. Therefore, the electrons in the iron core have to be described according to Fermi-Dirac statistics. In other words, we have the formation of an iron white dwarf right at the center of the star. Now, within a day or so, or within a few hours, in fact, the mass of this iron core will increase to 1.4 times the mass of the Sun, which is the limiting mass for white dwarf configurations, where gravity is supported by the degeneracy pressure of the electrons. What happens is the following. When the mass of the iron core increases, the central density will increase. If you remember Chandrasekhar's theory of white dwarf, the central density is 6 times the average density, which is proportional to the square of the mass. And therefore, as the mass of the core increases, the central density will increase. And when the density reaches 10 to the power 11 grams per cubic centimeter, or 4.3 times 10 to the power 11 grams per cubic centimeter, neutronization of matter will begin. Protons will absorb electrons, and neutrons will be formed, and neutrinos will be emitted. Now, in this process, electrons begin to disappear because they are absorbed by the protons. And as the electrons disappear, the pressure due to the electrons, which supported the star against gravity, decreases. Why? Because the pressure of a degenerate electron gas is proportional to density to the power 5 by 3, or 4 by 3 if it is relativistic. Therefore, as the density of the electron decreases, because the electrons are disappearing, the pressure, degeneracy pressure decreases, and therefore the core of the star will contract more rapidly, resulting in an acceleration of the neutronization of matter, and there will be a positive feedback. As the electrons disappear, the core begins to collapse faster and faster and faster, and there will be a dynamical collapse. So let us see what computer calculation tell us about the nature of this dynamical collapse. So let us look at the collapsing core. What I have shown here is just the iron core, and I have divided the iron core into two regions, the inner region and the outer region, for a very specific reason. What calculations tell us, what is plotted on this inset, in the vertical axis is the radial velocity of the collapse, and what is plotted on the x-axis is either the radius or the Lagrangian mass coordinate. In other words, the mass contained within a radius small r. So as r increases, the mass increases. So I could either plot it as a function of radial distance r or the Lagrangian mass coordinate, and there is no need to get confused about it. So now let's see what I'm trying to tell you. What computer calculations show is that the inner part of the core collapses homologously. What does homologous collapse mean? As the inner portion of the core collapses, the density profile is maintained. The density as a function of r is maintained even as the core contracts to smaller and smaller radius. This is known as homologous collapse. But the outer regions of the core are free falling. They are not collapsing homologously. They are free falling as if I dropped a stone. That is indicated here. This is the inner portion of the core is collapsing homologously, and the velocity increases radially with r. That's what I've indicated by the length of the arrow increasing. And the outer regions of the core is collapsing freely, and that means that the radial velocity decreases as you go to larger and larger radii. So that's the signature of free fall. It comes from Newton's laws. So let's repeat this once more. I'm considering a degenerate iron white dwarf whose mass is the Chandrasekhar limiting mass of 1.4 times the mass of the Sun. It collapses. The inner portion of the core collapses homologously, and even as it collapses, the outer portions of the core is collapsing freely, falling freely. So this is what will transpire, and I've shown this by a series of pictures. This is what I just said. Inner core collapses homologously. The outer core collapses freely, falls freely. Now the inner core, when it collapses to the radius of a neutron star, cannot remain as a stable neutron star, because look at it this way. If I go to the terrace of a building, of your apartment building, and drop a tennis ball, it has an enormous amount of potential energy, and as it comes down to the surface of the Earth, the potential energy decreases. But I haven't taken away the potential energy, and therefore the tennis ball will bounce back. But if I drop a ball of clay and I drop it, then it will not bounce back. That's because the potential energy has been taken away to account partly for the splash that it creates, a huge thud it produces, and by the deformation of the ball. It's no longer spherical, it is flattened. So the key principle is, in order for the collapsed core to remain collapsed and in equilibrium, I must be able to take away the gravitational binding energy. And I have not done that so far. So what the core does is bounce back just as a tennis ball will bounce back. Even as the inner portion of the core bounces back, it finds the outer portions of the core is still falling in freely. Therefore, the rebounding inner core meets the infalling outer core and drives it outwards. And in the process, a shock wave is created. And what one believed for 30, 40 years is that this shock wave blows apart the star. In other words, the binding energy that is released when the inner portion of the core collapses and forms a stable neutron star, that binding energy has now gone into expelling the envelope of the star, which is the supernova explosion. So according to the party line, the core collapses, a stable neutron star is formed, and a shock wave drives the envelope, and that is the supernova explosion. So that was the party line for more than 30 years. To repeat once again, the shock wave from the core rebound exploded the envelope of the star. Sounds very logical and very convincing. But in actual computer calculation, nothing like this happened. There was no stellar explosion at all. What calculation showed is that the shock, yes, a shock is formed, but the shock simply stalls and there is no explosion. It's like a Diwali firecracker, the wick burns and then nothing happens. It is a dud. So something else was happening because nature manages to explode massive stars. Now this great puzzle took a long time to be resolved, and it took a grand old man, the great Hans Bethe, who was 90 years old at that time, still very active, to come up with the explanation for how a star actually manages to explode itself. And that has to do with the role of the neutrinos. So when a core roughly of the mass of the sun, 1.4 times the mass of the sun, collapses and forms a neutron star, you have converted 10 to the power 57 protons into 10 to the power 57 neutrons. There were already neutrons, but you have created new neutrons. For every neutron that you create an electron neutrino. Right? Neutron decays to a proton plus electron antineutrino. So 10 to the power 57 electron antineutrinos would have been formed. And we thought that these neutrinos interact so weakly with the rest of the star that it will simply escape. The neutrinos simply escape. So it was left to the shock wave, the piston, to blow apart the star, and that was not doing the job. Now what Hans Bethe pointed out is that you haven't done the physics properly. You have assumed somewhat prematurely that the neutrinos will simply escape from the star. He pointed out that while calculating the neutrino cross-section with the stellar matter, one must take into account all processes that are allowed by the unified electroweak theory. Please remember, the theory of beta decay was first discovered by Enrico Fermi in 1934, and that is shown over there. Neutron decays to a proton, electron, and an electron antineutrino, or proton absorbs an electron and turns itself into a neutron and a neutrino. Now, this neutrino in Fermi's theory had a certain cross-section for interaction with ordinary matter. Now, what Hans Bethe pointed out is, but you shouldn't be using Fermi's theory of beta decay. You should be using the theory of Salam, Weinberg, and Glashow, which is electroweak theory, a unified theory which incorporates both electromagnetism as well as weak interactions. I shall say more about this when we discuss cosmology. But for now, please remember that there is such a thing as a unified description of electromagnetism and weak interaction, and Hans Bethe pointed out that you must calculate the neutrino cross-section according to this theory. And when they did that, it turned out that the mean free path of the neutrinos was comparable to the size of the core, when the density reaches about 10 to the power 10 grams per cubic centimeter. If you remember from our earlier lectures, I pointed out that even at a density of lead, the cross-section, the mean free path of the neutrinos will be many light years. In other words, neutrinos will travel for many light years without interacting with matter, even at the density of lead. But here we are not dealing with the density of lead, we are dealing with the density of 10 to the power 10 grams per cubic centimeter. And if you calculate the cross-section according to unified theory of electroweak theory, then it turned out that the mean free path of the neutrino is comparable to the size of the collapsing core. Therefore, the neutrinos act as an effective piston. If you remember, photons in a star act as a piston. That is why radiation pressure helps to support the star against gravity. But one never thought neutrinos would behave like a gas, exert pressure. But if the cross-section is very large and if the mean free path is very small, then just as photons do in a star, neutrinos will act as an effective piston. They behave like a gas exerting pressure. And so it turned out that it is the elusive neutrinos that actually blow up the star after the birth of the neutron star. So let's look at this picture. This is the collapsing core, this is the inner core, and you have formed a neutron star. And these dashed lines are the neutrinos. So let's look at this carefully. So here is the outer core, which is falling freely. Surrounding the outer core is a silicon burning shell. Silicon is still being converted to iron group of elements. And there is a shock wave, as was promised before, due to the bouncing inner core. And the neutrinos, which we thought would have escaped to infinity, are now trapped inside the core because their mean free path is comparable to the size of the collapsing core. Now we have a situation like photons in the sun. There is an outer radius which we shall call as the neutrino photosphere. So inside the photosphere, the neutrinos are rattling around, doing a random walk, and only when they come to the photosphere, they will escape to infinity with the speed of light. So the neutrinos, till they reach the photosphere, are acting as an effective piston, helping to distend the core of the star and propelling it outwards and creating a stellar explosion. So there are three definite predictions of this core collapse scenario for the supernova explosions of massive stars. The first prediction is that there should be a burst of neutrinos, a burst of 10 to the power 57 neutrinos with a total energy of 10 to the power 53 ergs, which is the binding energy of a neutron star. The second prediction is that there should be a neutron star at the center of the supernova ejecta. And the third prediction is that the mass of the neutron star must be very close to the Chandrasekhar limiting mass for a white dwarf, which is 1.4 times the mass of the sun. So you would expect the neutron star at the center of the site of the explosion to have a mass very nearly 1.4 times the mass of the sun. So what do observations tell us about these three predictions? Well, let's look at it. On the 23rd of February 1987, this star at the tip of the arrow exploded in the Large Magellanic Cloud, which is the nearest galaxy to us. And this is the supernova. Now, this was seen with the naked eye by a car mechanic in New Zealand who was an amateur astronomer. He knew the southern sky absolutely by heart, and then suddenly he saw a star and he knew that this was a supernova. Immediately he alerted observatories all over the world, and astronomers started observing this supernova. At that instant, in Japan, deep in the mine in a place called Kamiokande, do you remember the Super Kamiokande detector deep underground that was set up to detect solar neutrinos? Here are the thousands of photomultiplier tubes, and here are three astronomers in a small dinghy as the water is being filled up in the Kamiokande detector. To recall for you the kind of scattering that the Kamiokande detector detects, it is electron-neutrino scattering. A neutrino interacts with an electron, any kind of neutrino, electron neutrino, muon neutrino, or tau neutrino. In the case of a supernova explosion, we are only talking of electron neutrino because we are talking of proton plus electron going to a neutron plus electron neutrino. And what happens is that the neutrino is now scattered more or less in the forward direction, and the electron gets a kick and it is set off in motion at relativistic speeds, again more or less in the forward direction, and the electron is now going at a speed which is greater than the phase velocity of light in water. Therefore, it emits a cone of Cherenkov radiation. This is the optical analog of a shock wave. So this is what we discussed before. So if 10 to the power 57 neutrinos had been produced in the explosion of that particular star in the Large Magellanic Cloud, then a fraction of those neutrinos should have been detected by this Kamiokande detector, which was of course set up for an entirely different purpose. And lo and behold, it did detect a burst of neutrinos exactly when the star exploded. This is relative time on the x-axis. This is time zero when the star exploded. And you see there is clearly a burst of neutrinos. And the total energy, the energy distribution of the neutrinos as well as the total energy agreed precisely with what theoretical calculation had suggested. And not surprisingly, a few years later, in year 2002, Masatoshi Kushiba, who was the leader of the team of the Super Kamiokande experiment, was awarded the Nobel Prize for Physics for this very remarkable discovery of the burst of neutrinos from a supernova explosion of massive stars. So the first prediction has been verified. The second prediction was that there should be a neutron star at the center of the supernova explosion. And there it is, a neutron star right at the center of the Crab Nebula. This is an X-ray image taken of the Chandra X-ray telescope, and you see the pulsating X-ray emitting neutron star right at the center of the supernova remnant. The third prediction was that the masses of the neutron star produced in supernova core collapse should be equal to the Chandrasekhar limiting mass of 1.4 times the mass of the Sun. And what I have shown here is the masses of many neutron stars plotted in the y-axis, and these are the various neutron stars of different systems. The error bars and the measurements are plotted, and here is 1.4 times the mass of the Sun. So you notice that here are measurements of binary neutron stars, where the error is as small as the size of the inverted triangle. These are the most accurate measurements of the neutron stars. And you notice that in all cases, the masses of neutron stars are bang 1.4 times the mass of the sun. So all the three predictions made in the core collapse scenario for type 2 supernovae as well as type 1b supernovae have been spectacularly confirmed. Now, let us look at another aspect of this supernova explosion. And that is that these explosions need not be spherically symmetric, although when we draw pictures, we think of the core collapse to be perfectly spherically symmetric and the explosion to be perfectly spherically symmetric. For one reason, the collapsing core is rotating. Therefore, spherical symmetry is violated right then and there. But more importantly, you have very strong reasons to believe that the explosion will be highly asymmetric. Why? Now, what I showed before, what I've shown here, is inside the neutrino photosphere, you have a gas of neutrinos. They're rattling around because their mean free path is very small compared to the size of the core. Now, these trapped neutrinos are pushing the infalling outer core. So you have a light fluid pushing a heavy fluid. We'll come back to this toward the end of this lecture. This results in what is known as Rayleigh-Taylor instability. The light gas pushes heavier gas. The lighter gas becomes unstable to convective instabilities. These are known as Rayleigh-Taylor instabilities. So convective cells form inside the collapsing core. Now, these convective cells clearly define a particular axis. And there could be clearly an asymmetric supernova explosion because of these turbulent motions inside the neutrino photosphere. So this asymmetry, which you expect on very general grounds, which we never entertained before neutrinos were brought into the picture, and neutrinos forming an effective piston like a gas, becoming turbulent due to Rayleigh-Taylor instabilities, such an asymmetric supernova explosion can have several dramatic astrophysical consequences. To begin with, there could be a burst of gravitational radiation, as I had discussed when we discussed gravitational radiation. Now, although this has been expected for a long time, gravitational radiation from a collapsing star, there has been no detection of gravitational waves as yet. But these are still early days of neutrino astrophysics. But it's an exciting possibility to look forward to. But there is a second interesting and exciting astrophysical consequence of an asymmetric supernova explosion. And that is bound neutron star pairs such as the Hughes-Taylor pulsar or the double pulsar. The very fact that two neutron stars were bound is clear evidence for an asymmetric supernova explosion. Why? I explained this in great detail when we discussed binary evolution, but let me very briefly recall for you what I said then. When a star in a binary system explodes, you have to ask the question, will the binary be disrupted? And the answer is rather simple. For the binary to be disrupted, the mass ejected, delta M, must be greater than half the total initial mass. If the initial masses of the two stars were M1 and M2, let us say M2 explodes and ejects mass delta M, then only if delta M is greater than 1/2 of M1 plus M2, the binary will be disrupted. So when the second star in a binary system explodes, I argued that delta M will be greater than 1/2 M1 plus M2. Therefore, although the binary will not be disrupted in the first supernova explosion in a binary, it will be disrupted in the second supernova explosion in a massive binary. In rare cases such as the Hulse-Taylor binary pulsar or the double pulsar and several others now, the binary neutron star system remains bound. It is because of a great deal of asymmetry. Now, let's consider an asymmetric explosion of a solitary star. What will an asymmetric supernova explosion do? It will give a kick to a neutron star. Since the neutron star is not at the center of a spherically symmetric explosion, it will recoil and it will acquire large space velocities. It is now very well established. Hundreds and hundreds of pulsars have been measured with large space velocities. These space velocities must have surely been imparted at the time of their birth. And radio astronomers tell us that young pulsars have space velocities of the order of 400 kilometers per second, sometimes even as large as 1,000 kilometers per second. Therefore, these large space velocities of isolated neutron stars is a clear signature of asymmetric supernova explosion, which can happen if the neutrino photosphere becomes really Taylor unstable. Now let's go back to this question of type 2 supernova explosions with strong hydrogen lines, H alpha, H beta, H gamma, and type 1b supernova explosions which have no hydrogen lines but strong helium lines. We have to try to understand this. And there is a very simple and easy explanation for this. In fact, we have discussed this in our lectures when we dealt with binary evolution. So let us briefly discuss what we said then. Let us consider a massive binary consisting of 25 solar mass star and a 10 solar mass star. This is a 25 solar mass star, this is a 10 solar mass star. The more massive star evolves faster, fills its Roche lobe, and transfers much of the mass to the less massive star. So the more massive star evolves fast, fills its Roche lobe, and transfers mass to the less massive star. It then becomes the less massive star. The 25 solar mass star now becomes the less massive star. Its mass is now only 8.5 solar mass star, but it has transferred the rest of the hydrogen envelope to the companion star, which now is no longer 10 solar mass, it's now 26.5 solar mass star. Now this helium star is overluminous and it will evolve very fast. And this is of course the famous Algol system. The less massive star being more evolved, and this will now explode into a supernova explosion. When this less massive star explodes, what you will find in the ejecta is only helium. There is no hydrogen envelope anymore because all the hydrogen has been transferred to the companion star. Therefore, the helium star leaves behind a neutron star, and in the ejecta you will have only helium and no hydrogen lines. Now, the ejecta will not have any hydrogen, it will have mainly helium. This is the type 1b supernova. There is no hydrogen because it is an explosion of the less massive star in a closed mass transfer binary system. Now, with the explosion of the second star, this star over there, or the explosion of a solitary star, in both cases, the ejecta will be rich in hydrogen because there is a large hydrogen envelope, and therefore the ejecta will show strong hydrogen lines. So that is the explanation for why type 2 supernovae, which are either the explosions of solitary massive stars or the second explosion in a massive binary, shows strong hydrogen lines, H alpha, H beta, H gamma, whereas type 1b supernova, which are the explosions of the less massive helium star in a massive binary, show only helium lines and no hydrogen lines. Now let's go to type 1a supernovae. What we have discussed so far is the explosion of massive stars. A neutron star is produced in the center, and the binding energy release in the form of neutrinos pushes the envelope and creates a supernova explosion. Type 1a supernovae, on the other hand, are the result of a white dwarf being pushed over the Chandrasekhar limit. Now, a stable white dwarf by definition has to have a mass less than the Chandrasekhar limiting mass. So how do you accrete mass and push it over the Chandrasekhar limit? This can happen if you have two white dwarfs going around each other around a common center of mass in a binary system. It will emit gravitational radiation. And given hundreds of millions of years, these two white dwarfs will spiral into one another, coalesce, and the mass of the white dwarf will exceed the Chandrasekhar limiting mass, and there will be a stellar explosion. And this cartoon tells you what will happen. Two spiraling in white dwarfs finally coalesce and create a type 1a supernova explosion. And they spiral in because of the emission of gravitational radiation and eventually merge, resulting in an explosion. And the remnant of the merger could either be a massive neutron star or a black hole. You remember my lecture on the maximum mass of a neutron star. We expect the maximum mass of a neutron star, according to modern physics, to be around 2 solar masses. We don't know the exact number. It's a very hard problem. So, when the two neutron stars coalesce and expel the rest of it, what remains, if that mass is less than the upper limit for the mass of the neutron star, then you will have a marginally stable massive neutron star. Otherwise, what you will have is a black hole. But we are not concerned with that in this lecture. So what we are concerned is that the resulting explosion is a type 1a explosion whose light curves of many supernovae are shown in this picture. Now, it turns out that if you make corrections for the distance and various effects of the interstellar or intergalactic reddening, and put all the light curves on top of one another, then you find that the type 1a supernova light curve are like standard candles. In other words, at the maximum, the luminosity of a type 1a supernova seems to be the same. Whereas at the maximum, the luminosity of a type 2 supernovae or type 1b supernovae can vary quite significantly. Observations of hundreds and hundreds of type 1a supernovae tells us that if you correct for various external effects, the luminosity at their maximum is like a standard candle. And therefore, it has an immense importance in cosmology, as we shall see. It is using these standard candles that astronomers discovered that our universe is accelerating. We'll come to the story a little later. Now, we shall turn to supernova remnants. What are supernova remnants? It is the ejecta of the stellar explosion. What is shown here is the remnant of the explosion that occurred roughly 300 years ago in the constellation Cassiopeia. This most famous stellar explosion is known as the stellar remnant of the explosion is known as Cassiopeia A. These are known as supernova remnant. We know hundreds of such supernova remnant. So let's try to understand the physics of some of these. Now, when the star explodes, the ejecta, which is moving very rapidly, with speeds of the order of 20,000, 25,000 kilometers per second, will expand freely according to Newton's first law. The velocity will be constant. That's because the mass that is swept up by the ejecta is like a piston expanding into the interstellar medium, it's like a bulldozer expanding, moving in the interstellar medium. It will accumulate interstellar matter in front of it. But the mass of that swept up matter is so small compared to the mass of the bulldozer that the bulldozer doesn't slow down at all. It expands according to Newton's first law. The velocity is a constant and the diameter is proportional to the time. The diameter is proportional to the time. Now, when the ejecta has swept up a lot of mass from the interstellar medium, such that the mass that is in front of the bulldozer is far greater than the mass of the bulldozer, then the bulldozer doesn't remember anything. The whole dynamics is governed by the mass that has been swept up by the bulldozer. So the ejecta no longer remembers anything about the initial velocity or the initial momentum. It only remembers the energy that it had, the kinetic energy of the order of 10 to the power 51 ergs. Now, as this ejecta with an enormous amount of swept up mass, which is far greater than the mass in the ejecta, expands, what is conserved is the entropy. So it is an adiabatic expansion. Now the swept up matter will be shock heated. You remember there's a shock from the blast wave because the velocity of the blast wave far exceeds the speed of sound in the interstellar medium. The shock wave heats the interstellar gas to a temperature of 10 million or more degrees. And at such high temperatures, radiation is inefficient. Radiation is essentially due to bremsstrahlung, which is not a very efficient radiation mechanism. Radiation due to electronic transitions is not possible at such very high temperature. Therefore, the total energy is conserved. In other words, the expansion will be isentropic or adiabatic. Now, the expansion will be self-similar. The supernova remnant has so much mass swept up, it really doesn't matter what is the mass in the ejecta. It will go through a phase of self-similar expansion. You wouldn't be able to tell by just looking at it whether it is small or big, because its expansion will be self-similar. If you understood what I said, fine, otherwise don't worry about it. Now, it is possible to show that in this phase of adiabatic expansion, the diameter of the supernova shell, supernova remnant, will no longer be proportional to the time as Newton's first law, but it will be proportional to time to the power 2 by 5. Don't worry about it. I'm just stating this. This is adiabatic expansion. This will be followed later by a phase where entropy is not conserved. The gas is cooled, it is radiating, the tremendous amount of energy is being lost. What will be conserved will be the temperature. It will be an isothermal expansion of the piston. Now, in an isothermal expansion, it turns out what is conserved is not the velocity or the energy or entropy, but it is the momentum that is conserved. Now, when the temperature of the gas drops below 1,000,000 degrees, various heavy ions present can capture electrons, and you can have transition between various lines, various excitation levels of this ion, and these various transitions give rise to X-ray emission, and the gas will quickly cool. And as the gas cools, it will get more compressed, and it will cool even more, and there will be a positive feedback, and the gas will get highly compressed. And in this phase, just for completeness sake, let me tell you that the diameter of the supernova remnant will be proportional to T to the power 1 by 4. Now, I know I've hit you with too many things which you're unfamiliar with very fast, but it's really not important. Don't worry about it. All I want you to remember is the following. The supernova ejecta is like a bulldozer moving in the interstellar medium. It will sweep up the interstellar gas. There will be several phases of expansion. There will be a free expansion phase. There will be an adiabatic expansion. There will be an isothermal expansion. Then this piston will expand to larger and larger radius. After thousands and thousands of years, the radius of the supernova remnant will become many light years, hundreds of light years, and it will eventually run out of steam and come to a stop. It will come to a stop when the pressure inside the supernova bubble is equal to the interstellar pressure outside the supernova bubble. So here is the expanding debris of the star that Kepler saw exploding in the year 1604. What I'm saying is, this is an X-ray image from a 10 million degree gas. After thousands and thousands of years, this supernova remnant, like all other supernova remnant, will expand to a size of hundreds of light years and will come to a stop and eventually break up and lose its identity. Now, let us go back to the supernova that the New Zealand car mechanic saw explode on the 23rd of February 1987. Now here is the baby supernova remnant captured 30 years after the explosion. No one has seen such a young supernova remnant before. The youngest one is the Cassia supernova remnant, which is 300 years old. So we don't know what any of these looked when it was very young. Here is a 30-year-old supernova remnant. And what are the various pictures? This is, on the left is synchrotron radiation, radio radiation from relativistic electrons gyrating in the magnetic field. This is dust seen in millimeter wave radiation. This is visible radiation. This is X-ray radiation seen by the Chandra X-ray telescope, emitted by million degree gas. And this is the composite image of radio, X-ray, and infrared and millimeter wave radiation. So that's what the baby supernova remnant looks like. Here is a supernova remnant which is 1,000 years old, the famous Crab Nebula. This is the visible emission from supernova remnant, and you see inside the diffuse blue amorphous emission, that is the synchrotron emission from the relativistic electrons which were pumped into the nebula by the central pulsar. And what you see on the right is a radio emission from Crab Nebula. The radio emission is synchrotron radiation emitted by the relativistic electrons in this nebula, pumped by the central pulsar, gyrating in the magnetic field, which was also supplied by the central pulsar, if you remember my lecture on pulsars. Now here is a very old supernova remnant, the Whale Nebula in the constellation Vela. It's about 10,000 years old. There is a pulsar, a radio pulsar, and an optical pulsar. It's pulsating with a period of 89 milliseconds, still quite young, it's only 10,000 years old. And what you see is already that the supernova remnant is beginning to lose its identity. It's not like an expanding piston anymore. It has a sort of a lacy structure. Eventually, it will lose its identity. Now, let us look at some interesting aspects of this expanding shock wave. There's a blast wave which drives a shock into the interstellar medium. So here you have the expanding ejecta. I showed it in one dimension, but you're supposed to imagine it in 3 dimensions. Now, here is the interstellar medium, unperturbed interstellar medium, and in front of the ejecta, there is a shock wave. The shock wave is traveling faster than the speed of sound in the interstellar medium. So this interstellar medium doesn't know anything about this shock wave till it actually hits it, because no sound wave can reach. Suppose there is a blob of interstellar matter here, no sound wave will reach that before the shock wave reaches it, because shock wave is going faster than the speed of sound, and information travels at the speed of sound. So let us, instead of the shock wave expanding into the interstellar medium, let us go to the frame of reference in which the shock wave is at rest. So what you will see is that the interstellar gas is coming towards you with a velocity v1, and it has a density ρ1, it has a temperature T1, which is characteristic of the interstellar medium in that vicinity. The precise values don't concern us. The important thing is, pretty soon, this gas will go behind the shock. And when it goes behind the shock, it will be heated and compressed. And the temperature of the electrons now will be about 10 million degrees, and this gas will be emitting X-rays. And that is the X-ray emission that we saw from supernova remnant like Tycho's remnant, which was detected by Chandra X-ray Observatory. That is the million or 10 million degree gas which has been heated by the shock wave of the expanding bubble. Now, let's look at it in 3 dimensions, or projected onto 2 dimensions. You have the ejecta, which is that annulus over there. Ahead of the ejecta, the outer circle is the shock wave expanding into the interstellar medium. And what you have inside the ejecta is matter from the interstellar medium which has been swept up, compressed and heated by the shock wave. So inside of the supernova cavity is not empty anymore. It is filled with gas. This gas is known as the coronal gas because its temperature is similar to the temperature of the solar corona, which is about 10 million degrees. Its density is very, very small. It's only about 0.003 atoms per cubic centimeter. Again, very similar to the corona of the sun. But it emits X-rays. So the supernova bubble is now filled with 10 million degree gas. Now, that's what you see. Now, here is Tycho supernova remnant, which Tycho Brahe saw in the year 1572. It, of course, emits radio radiation from synchrotron radiation. We'll come to that presently. But what you see here is X-ray emission, Bremsstrahlung, electrons colliding against ions in the 10 million degree shock-heated gas. Here is the X-ray image, again with the Chandra telescope, of the supernova remnant that exploded in the year 1006, which was described very vividly by Arabian astronomers, if you remember our discussion of the guest stars. Now here is the spectacular composite image of Cassiopeia A, a 300-year-old supernova remnant. Its composite image, which consists of radio emission, which is synchrotron emission, infrared emission, which is from the dust, and X-ray emission, which is the Bremsstrahlung. Now, this is just X-ray emission, and what you see at the center there is the neutron star. Now, the ejecta consists not only of the elements synthesized in the star during various stages of the nuclear fusion cycles, which ended when iron 56 was synthesized, because that's the most stable nucleus, and then you had a collapse of the core and a supernova explosion. But it also contains elements heavier than iron. After all, If you look at the Earth, there are elements heavier than iron. There is gold, platinum, uranium, thorium, and so on. How were they synthesized? They were not synthesized in the star. So the conventional belief is that these were synthesized when the star actually exploded. I shall discuss that in my first lecture on cosmology, so we shall not pursue this any further. Now, those elements are synthesized by capturing neutrons in a very rapid process. Now, let us look at what observation of this Cassiopeia A with the Chandra X-ray Observatory tells us. What you see here is the X-ray spectrum, intensity on the y-axis and energy or wavelength on the x-axis. And what you see are the various emission lines. You see oxygen, neon, magnesium, silicon, sulfur, argon, calcium, and of course the famous iron at 6.4 kilo electron volts. So this is a direct confirmation that all these elements were synthesized in the star that exploded, just as we had said in our theoretical discussion of stars. Now, the Chandra X-ray Telescope has a transmission grating. And the beautiful thing about the transmission grating is you can image the supernova remnant at different wavelengths by looking at different orders of transmission through the transmission grating. If you remember your grating spectra from your undergraduate days. So what you see here are actually images of Cassiopeia A taken in the line of silicon, taken in the line of sulfur, calcium, iron, and so on. This is absolutely extraordinary. If you had shown me such a if you had told me about such a spectrum 20 years ago, I would have said it's pure science fiction. But here is the real images of the Cassiopeia supernova remnant taken in the lines of the various elements using the power of a transmission X-ray grating. The supernova remnants are also the sites of acceleration of cosmic rays. We know cosmic rays come to the Earth. We know cosmic rays are produced by pulsars. We discussed that at length. The Goldreich-Julian mechanism where particles are pulled out of the surface and accelerated along the electric field parallel to the magnetic field, and they flow along the open field lines into the interstellar space. Cosmic rays are also accelerated by accretion disk around black holes in active galactic nuclei, quasars, and so on. But supernova remnants such as this are also powerful accelerators of cosmic rays. How are particles accelerated to ultra-relativistic speeds in cosmic rays? In supernova remnants, They are accelerated by a process that was first discussed by Enrico Fermi in 1949. In 1949, one didn't know about supernova remnants or anything like that. Crab Nebula was known, but we didn't know at that time that it was actually the remnant of a supernova explosion. But Fermi was studying cosmic rays, and he was wondering, where do cosmic rays come from? And he wanted a mechanism whereby electrons could be accelerated to speeds comparable to the speed of light. And a variant of that mechanism, I'm going to explain to you in a moment. But first, look at what I have shown on the right over there. Here is the Earth. And what do you normally find? Above the Earth's surface, there is an atmosphere. And the density profile of the atmosphere is given by Boltzmann distribution. Okay? E to the power mgh over kT, which gives you a density profile where the heavier elements are lower in the atmosphere and lighter elements are higher in the atmosphere. And this is what you would expect in hydrostatic equilibrium. But under certain meteorological situations, the following situation can happen. What you have immediately above the Earth is lighter atmosphere, hotter atmosphere, and what you have sitting above it is colder and heavier atmosphere. So this is a very unusual situation. So what you have is gravity, acceleration due to gravity acting in this direction, and the pseudo force due to gravity acting in that other direction. Remember, the pseudo force acts in a direction opposite to the direction towards the center of the Earth. If you're not familiar with this concept of pseudo force, by the way, when you stand on the lift, what you experience is the pseudo force. What you see is something that's pushing you up, preventing you from falling freely towards the center of the Earth. Please refer to Feynman Lecture Volume 1, where he discusses gravity and pseudo force. A beautiful discussion. Like in all topics, let me once again say, please refer to Feynman Lectures Volume 1, 2, 3. They're all available for ridiculously low price of about 175 rupees each, published by, originally by Springer Verlag. An Indian edition exists. Do go out and buy them. Okay, so what we know, and when we heat a container, a beaker of water, is that when a lighter element pushes the heavier element, then the heavier element becomes unstable. This instability was first discussed by Lord Rayleigh and G.I. Taylor in Cambridge, and this is known as Rayleigh-Taylor instability. So one example of that is when you heat a pot of water. Initially, heat from the bottom to the top is by conduction, and the water is very quiescent. Afterwards, when the temperature gradient exceeds a certain critical value, you see convective cells form. Hot bubbles rise up and cold bubbles come down, and this is known as Rayleigh-Taylor instability. Well, the purists will question this. They'll say this is really not Rayleigh-Taylor instability, but for our purpose, this is good enough. So when a lighter fluid pushes the heavier fluid, then you have turbulence. This is why when the neutrinos pushed the infalling outer portion of the core, which is still infalling, you had convection, which resulted in an asymmetric supernova explosion. So all I'm trying to say is this compressed, swept up gas immediately behind the ejecta and the shock wave becomes convectively unstable. So the convective cells that are formed. Now the ejecta has frozen in magnetic field. Where did this magnetic field come from? Well, the star had magnetic field. There were current loops in the star which gave rise to magnetic field. And because the matter is highly conducting, you cannot destroy this magnetic field unless the currents themselves decay due to ohmic dissipation. Therefore, the ejecta have magnetic field. Now, this magnetic field will be tangled up and completely random. But now, a certain order is brought into it because the fluid becomes highly convective, and therefore these magnetic field lines are predominantly stretched in one particular direction. It's like a particular sweet that is made in South India. I don't know the name in English or Hindi, but this is what they do. They take this dough and keep on stretching it in a direction, so you form needle-like structures. So what you'll have are convective cells, which results in compression and amplification of the magnetic fields, predominantly along the axis of the convective cells. So then what happens is that, okay, so let's repeat. In a gravitational field, this Rayleigh-Taylor instability arises when a heavier fluid is supported by a lighter fluid. When a lighter fluid is pushing or accelerating a heavier fluid, this instability arises, and this is very common in astrophysics. Convective cells form in the swept up matter. Motion in the cells stretch the magnetic field and amplify the magnetic field in one direction. Now, electrons scatter off magnetic fields. Now, in any given scattering of an electron in a magnetic cell, it may gain energy or it may lose in energy. Therefore, there will be a random walk in energy. Energy increases in some collisions, energy decreases in some collisions. But in a stochastic process, Fermi showed, energy will always increase. You remember the picture that is drawn of a random walk with a drunk man starting his walk at a lamppost. Yes, he is drunk and he walks in a random fashion. Please remember, he never comes back to the lamppost. The distance from the lamppost always increases. This is the consequence of second law of thermodynamics, a consequence that in a stochastic process, the distance will always increase. Here we are talking of a random walk in energy space. The energy of the electron either increases, decreases, increases, decreases, increases, decreases. But eventually, in a systematic manner, it will increase. And the electrons will increase and acquire energy such that the energy of the electron comes into equipartition with the energy of the magnetic cells, b squared over 8 pi. Fermi was very fond of invoking equipartition theorems in many, many contexts. And this is a context in which he invoked equipartition to accelerate electrons by scattering them off. Well, this is not the problem he was addressing. He was talking about accelerating cosmic rays in our galaxy. But we are applying his arguments to the particular case of convective turbulent motion behind the shock wave in a supernova remnant. But nevertheless, we call this Fermi acceleration mechanism, and this is called the second order Fermi acceleration mechanism because this is stochastic acceleration. But there is also a first order Fermi acceleration mechanism, and the convective cell, what happens is you scatter an electron in a convective cell, the electron comes here, it is scattered outside the shock wave, then something else scatters it back inside the shock wave. It scatters off another cell, goes outside, comes inside, goes outside, comes inside. And so in each scattering, it gains energy, which is first order in V over C. Whereas in the previous mechanism, the gain in energy was proportional to V squared over C squared. Here, the gain in energy in each collision is proportional to V over C. But eventually, the electrons will be accelerated to relativistic speeds, and this is known as Fermi acceleration mechanism. Now, this Fermi acceleration mechanism is a very, very powerful mechanism, and it's the most convincing mechanism that we know of today in astrophysics to accelerate cosmic rays in any of the sources, except perhaps central engines like blazar or a black hole or a pulsar. In other situations, Fermi acceleration is the most possible mechanism to accelerate cosmic rays. Now, so to summarize, Enrico Fermi first suggested first-order mechanism in 1949 to accelerate cosmic rays in interstellar space by scattering off electrons of interstellar clouds with frozen-in magnetic fields. He was severely criticized, and then he came up with stochastic acceleration, which cannot be wrong. And the beautiful thing about the Fermi acceleration mechanism is that it gives you a power law spectrum of electrons. What I mean by that is that if I plot the number of electrons on the y-axis and the energy of the electron in the x-axis, then the number of electrons falls like this, and it is a power law. It's proportional to e to the power minus alpha, where alpha is some number of the order of 0.5 or 0.75. This is what we find in nature. This is what we find of cosmic rays. The Fermi acceleration mechanism naturally produces a power law spectrum of electrons. Now, if you remember, these electrons, when they gyrate in a magnetic field, which has been amplified behind the shock due to turbulent motion. It will produce synchrotron radiation, whose characteristic frequency will be decided by the energy of the electron and the strength of the magnetic field. And that's what produces the synchrotron radiation from supernova remnants, such as the Crab supernova remnant or the Vela supernova remnant. Now, the power law spectrum of electrons, if you remember my discussion of radiation from accelerated charges, a power law spectrum of electrons will produce a power law spectrum of synchrotron radiation. In other words, if I plot intensity of synchrotron radiation as a function of frequency, what I will find is that it will be a power law. And the power law will be nu to the power minus p, where this p will be related to alpha, which is the power law index of the number of electrons as a function of energy. If you remember that, fine. Otherwise, go back and listen to the lecture on radiation from accelerated charges. Therefore, the synchrotron radiation from supernova remnants, hundreds of them, clearly show a power law spectrum, which tells you that the radiation acceleration mechanism that is at work must be some variant of Fermi acceleration mechanism. Let's say here is a supernova remnant with a central pulsar on it. It will have two kinds of synchrotron radiation. There will be synchrotron radiation from a nebula like the Crab Nebula, which is produced by the pulsar. The pulsar supplies the particles, the pulsar supplies the magnetic field. So that's the Crab Nebula, for example. But you also have synchrotron radiation coming from the ejecta in many supernova remnants. Whether or not there is a pulsar in the center, this synchrotron radiation arises from relativistic electrons which have been accelerated in situ near the periphery of the supernova remnant due to Fermi acceleration mechanism, and they are gyrating in the magnetic field, which were amplified and created, compressed and amplified right in situ near the outer boundary of the supernova remnant. So here is synchrotron radiation from Tycho's supernova remnant. It's a power law spectrum, and there is no pulsar in the case of this supernova remnant, and therefore you don't see a Crab nebula-like emission in this case. So here is the same supernova remnant. This is synchrotron radiation from Tycho's supernova remnant. This is Bremsstrahlung X-ray radiation from the same supernova remnant, and what you see here is the hot 10 million degree gas which has been swept up by the expanding blast wave and heated and compressed by the shock wave. Okay, fine. Now, in a few moments, let me say something about the impact of all this on the interstellar medium. I apologize for running over time. Just a couple of minutes more. So what you have on a very large scale, if you look at the interstellar medium, you will find here and there bubbles of supernova remnants, bubbles created by supernova remnants. Some will be small and very hot, some will be big. They'll be filled with tenuous million degree coronal gas, density of the order of 0.003 atoms per cubic centimeter. So these are many light years across, and the distances between them may be, again, hundreds of light years. But given enough time, these expanding bubbles of supernova remnants will bump into each other. And what you will form are tunnels in the interstellar medium, long tunnels. And what do you have in the tunnel? You will have swept up, compressed, million degree or 10 million degree gas everywhere in these tunnels. So the interstellar medium, our raisin pudding, is now filled with these tunnels created by expanding supernova remnants. Now these expanding supernova remnants encounter interstellar clouds. It may be a giant molecular cloud, or it may be a hydrogen cloud, neutral hydrogen cloud, which is seen in 21 centimeter radiation. So here you have hydrogen clouds which have been swallowed by the expanding supernova bubble. Now this hydrogen gas will get hot, and slowly the cloud will evaporate and lose its identity. Now, this supernova shock wave will drive a shock into the giant molecular cloud and create an ionization front over there, and that will create star formation in this region. We discussed that when we discussed star formation at the outer periphery of supernova remnants. And we also discussed random motions of neutral hydrogen clouds. So a cloud is clobbered by an expanding supernova bubble and set in motion in random directions. So please remember, each supernova explosion deposits about 10 to the power 51 ergs worth of kinetic energy into the interstellar medium. In a galaxy like the Milky Way galaxy, a massive star explodes every 25 or 30 years. So the interstellar medium is enormously influenced by the supernova explosions and these expanding supernova bubbles. So molecular clouds are the nursery for new stars. When massive stars explode, the blast waves cause havoc in the interstellar medium. They form giant bubbles and tunnels. The sun and the planets are actually inside a local bubble. This is what observations tell us. Blast waves accelerate diffuse atomic clouds. The million-degree gas in the giant supernova bubbles will evaporate the clouds. And thus, the interstellar medium is not a serene raisin pudding. It's an incredibly violent and dynamic medium. So with that, we conclude this very rapid and condensed discussion of explosions of stars. And in the next lecture, we will change topic very dramatically, and we will discuss the gamma ray universe, a new frontier of astronomy. Thank you very much.